Hello, everyone. Welcome to PyData Global 2021. My name is Florian Rössler, and I'm very proud to chair this session. Please join me in welcoming Ehsan Totoni. He'll be talking about Bodo, supercomputing-like performance and scale for Python and Pandas. Ehsan is an entrepreneur, computer science researcher, and software engineer working on democratization of high-performance computing for data analytics, AI, and ML. Ehsan received his PhD in computer science from the University in Illinois at Urbana-Champaign. Working on various aspects of HPC and parallel computing, he then worked as a research scientist at Intel Labs and Carnegie Mellon University, focusing on programming systems to address the gap between programmer productivity and computer performance. Ehsan drives Bodo's mission to democratize HPC for data science with the belief that it should not remain a bastion of a select few experts. And as Moore's law begins to slow, it is Ehsan's vision to apply parallel computing principles to maintain computing's evolution. So over to you, and enjoy the talk.
Thank you, Florian. Excited to be here and introduce Bodo to the PyData community. I'm Ehsan Totoni, co-founder and CTO of Bodo, as Florian mentioned. We are a new platform for big data processing applications that brings simplicity of Python and performance of HPC together at the same time using a new inferential compiler technology that I will explain in a minute. So the problem we are addressing is the fact that in various organizations, development of data applications, such as machine learning, happens in Python using libraries such as Pandas, but it's typically on local files and laptops. But to scale the code to production, the Python code is typically rewritten in some other language, sometimes Java, Scala, C++, or Python APIs on top of a Java system, and with systems such as Spark to scale to production. Even then, things like Spark are far from HPC performance, high performance computing performance, and have a lot of inefficiencies. So extremely difficult to scale to production, and even then there are a lot of inefficiencies. Bodo is a new platform that can scale the same Python code to production without rewriting it. So Bodo platform is responsible for providing high-performance connectors, automatic parallelization of the code to scale on large number of cores, end-to-end optimization of the code, providing the right primitives such as join and so on, high-performance way under the hood, and integrating with various systems out there. So this is the Bodo platform at a very high level, and we will go to various details in this talk. But to get us started, to show how the code looks like, this code is from one of our partners, NASDAQ, and it's loading a large data set, Parquet data set from storage. And in that case, it was a Hadoop storage, filtering the data frame using some regular expression. They were interested in transaction of a certain, in certain sessions in the exchange, and calling the scribe, which gives a lot of statistics. So for this Python code, Bodo handles all of these operations, the same APIs as Pandas, and all the user needs to do is add this bodo.git decorator. So Bodo engine is just a Python package, conda install Bodo, as you can see, and you can launch this program on any number of cores. In this case, they use 224 with MPI exec, just you would do on any high performance computing system, but this can be done on any underlying infrastructure. Hadoop cluster, cloud, AWS, Azure, GCP, doesn't matter, and it can be in notebooks, as I will demo as well. So native Python APIs, no new Pandas-like API layers, more capabilities than something like Spark, because in Spark you don't have quantile calculation, for example, because quantiles don't fit the MapReduce parallel pattern, and you get HPC performance and scalability. So Bodo under the hood uses obviously Numba. For a lot of Python developer, Numba is a familiar tool for JIT compilation, but also Bodo supports MPI, which is standard for parallel computing and supercomputing applications. So our platform, as I mentioned, can be installed can be used on any infrastructure, on-premises, cloud, anywhere. And we support open source APIs, Pandas, NumPy, scikit-learn, because we are a compiler solution. We don't need to expose new APIs. And Bodo can be used on any storage. We're completely storage agnostic. CSV files on S3, Parquet files, Snowflake data warehouse, Hadoop, doesn't matter. And you can integrate with Bodo with any visualization tool out there. Here's a quick benchmark to show you how it works at a high level, how it compares to something like Spark. One of our customers is a big Fortune 10 tech company, and they use TPCx Big Bench. TPC is an organization, industry standard organization for benchmarking big data systems and databases. And for decades, TPC benchmarks have been standard for benchmarking. So our customer took this benchmark on a large AWS cluster with 125 instances with a total of 4,500 cores. So 4,500 cores, a large cluster, and they ran this benchmark on scale factor 40,000, which in TPC terminology means the total data set in memory is probably around 40 terabytes. So they optimized the Spark solution, which they use EMR solution of AWS manually with the Java tuning and parameters. But even after all these optimizations, Bodo without tuning was over 20 times faster than Spark on this large cluster. So this shows that Bodo is very good for use cases such as ETL, data prep, feature engineering, and these sort of applications that these benchmarks represent. But taking a step back, the problem for scaling code goes back to the old problem of simplicity performance gap that has been an open computer science problem for several decades. So on one extreme, you have high-level scripting code, used to be MATLAB, or now it's mostly Python, the favorite of programmers. So scripting codes are very simple to use, high-level APIs such as Pandas, but they are slow and single core. They don't scale natively. On the other extreme is high-performance computing code. Some advanced universities or national laboratories of various countries, such as the United States, there are HPC experts that write MPI code, very low-level MPI, Fortran, C++, and these codes scale to hundreds of thousands of cores, sometimes millions, but they are extremely difficult to write. Sometimes they take years. So there is a huge gap between simplicity and performance in programming, and that's what we tackle. The solution to this problem would be having a compiler that can automatically take the simple code and generate the fast code for you and essentially automate the process of an HPC expert. But this is a very difficult problem and has never been solved before. And that's what we have solved for the first time, we believe. So a regular compiler just translates your code, let's say C code, into a sequential binary. But Bodo's inferential compiler takes the human readable code, in this case Python, analyzes the code structure to understand its operations and the algorithm, optimizes the operations as much as possible, and translates the code into a fully parallel execution binary. And it's as if an HPC expert wrote the code for you, but it happens in real time and transparently. So that's the right solution, we believe, for scaling code. And this is the result of many years of research and development at Intel Labs, Carnegie Mellon University, where I was, and now at Bodo. So it's not an easy problem to solve. But because Bodo didn't exist, the industry went a different route, things like Spark, Dask, and Ray. So the way other systems work is that the Python code is rewritten in terms of some other APIs. So Dask APIs, Pandas-like APIs in Dask, or Ray Modin, or PySpark, if you will. So the code is written in terms of these APIs, and it runs on top of this library. And the way it's executed is that the program starts on the driver program. So the program is actually sequential. But when the high-level APIs are called, the library breaks up the computation into tasks, goes across the cluster, runs those tasks, and comes back the driver. We call this waves of tiny tasks model. And the problem is that these tasks have a lot of overhead to be scheduled and sent to the cluster, all the data that they need, and come back, and managing all these task dependencies and task graphs. So very high overhead distributed system approach, and we have a paper about this if you like more details. The way Bodo works is that the Python code is compiled to a native parallel binary with MPI, as if an HPC expert would write the code, and runs on bare metal. And the program is actually parallelized. There is no driver running the code. All the cores are running the code. They have their own chunk of the data, and they know what to do with their data. They know how to communicate and how to execute efficiently. They are not going to a centralized driver or master. And it's the MPI model and the so-called single program multiple data model that has been the standard of parallel computing for decades. So we believe Bodo provides a true parallel architecture solution, and this is the scientifically correct way to do parallel computing for data workloads that we are targeting. And task scheduling is not the right way. So at a very high level, there are two dimensions, simplicity and performance, for data systems and big data systems. And we provide simplicity of Python and performance of HPC, and we believe we are far away from other solutions in this space. And I will show benchmarks and use cases and examples to demonstrate. So based on these results, we believe Python should be used for hard data engineering problems. Python shouldn't be a prototyping language and all the enterprises, big companies rewriting the code to Java or C++ or Scala out of Python. With Bodo, the code can stay in Python, and Python can be faster than Java, and we are often significantly faster. So for difficult problems like ETL, data transformations, data cleaning, data prep on terabyte or petabyte data sets for feature engineering, that's where Bodo shines. For data engineering, the first step is always scalable I/O. How do you load this multi-terabyte data set into memory efficiently? With Bodo, the APIs are standard Pandas APIs. So the code looks like Pandas. You can say load this Parquet data set, which could be like a directory of a lot of pieces, or even CSV, it could be a directory of a lot of pieces, or load from Snowflake or this data warehouse using pandas.read SQL. And Bodo is responsible for loading the data in different chunks on different cores efficiently. So you don't have to worry about that. To show you an example of this, I think loading from Snowflake is a challenging operation, or any SQL system that we solved recently, and we just released the new Bodo version for it. It's challenging to load from SQL-based systems because if you have a large cluster of 10,000 cores, one approach would be to send 10,000 queries to the data warehouse to load different chunks. And we have found that this overwhelms even the most scalable systems such as Snowflake. So Snowflake released a new distributed fetch connector that we have been working with them in terms of design and implementation. And this new connector allows you to load the data in batches with just a single query. So one of the cores sends a query and gets a handle to these batches of arrow pieces, and different processors load their own batch or their own piece out of those batches. And this is a much more scalable and efficient way to load data from Snowflake. And we tried a few use cases where Snowflake was doing some of the data load itself with minimal computation, versus Bodo loading the data using this connector. And if the data, kind of the table is warm in Snowflake, it has a lot of caching capabilities, we are essentially equivalent to Snowflake in terms of loading the data out of the Snowflake storage layer, which is very exciting to see in such a difficult problem. So what are the limitations of Bodo? I think a lot of developers in the audience know about Numba and some of the limitations of compilation approach. The problem is that Python is not 100% compilable all the time. So there are cases where you can't assign data types. So the most important thing is data types and type stability. So some cases where compilation is not possible. On the left side, we had this example of using a flag, you can assign different types to a variable. And this would result in an error because the compiler can't assign a data type to this variable, doesn't know if it's integer or a NumPy array. So that's one case. And in Python, you can do a lot of crazy things, such as, a function is a variable, and you can, change the function variable and just call it. It's a callable object, but the compiler can't resolve the function and can't do its job. But please don't do that. These are not good program practices in a lot of cases. So the code has to be clean for the compiler to understand it at a high level and be able to figure out the data types. But the data engineers and developers who are familiar with things like Python or familiar with a typed language, I think they should be able to pick up Bodo quickly. But how does Bodo compare to other systems out there? There are just so many different things coming out on a daily basis that there's a lot of confusion in this area. And there are a lot of claims by various companies and projects in terms of speed and scale. And unfortunately, I found that a lot of these claims don't have evidence, or they have some overly simplistic benchmarks that are just a single join or a single group by that doesn't tell you too much about the capabilities of the system. So what we are proposing is just using standard benchmarks that have been used for data systems for decades. And it shows what we are targeting. We are targeting large data, big data, data engineering, ETL, those sorts of workloads. TPC benchmarks have been around forever. In particular, TPCH benchmarks have been used for a long time, and they're not too complicated. You can actually look at them and after a few minutes understand what they are doing. So what we did was that we translated these queries from SQL to Python, and it's open source. You can look at it. And we wrote versions for Dask, Ray, other systems, and compared performance. And we are obviously biased, and we are not Dask experts or Spark experts or Ray experts, but this is a starting point. I think this is much better than not having any benchmarks. And we invite everybody to look at what we did, take the code, run it yourself, let us know what we could do better for these benchmarks. But these are our benchmarks, and this is the way we benchmark. So you can look at the SQL code and Python code. I prefer the Python version, but it's subjective. Some people like SQL a lot more. I don't know. So comparison to Spark, I think Spark is the closest solution to Bodo for big data. We took TPCH with a scale factor 1000, which would be around a terabyte of data in memory, and used the 16-node cluster, which has 576 physical cores, not virtual cores. Typically there's one physical core per 2 virtual cores in these cloud infrastructure instances, and a total of 3 terabytes. And these instances have good networking and a fast networking option on AWS called EFA, Elastic Fabric Adapter, where processes can essentially, different cores can write into each other's memory directly. You don't even need to go through TCP and the network for doing that. It's much faster than regular networking. So very interesting capability on AWS for high performance computing. So for Spark, I have 3 examples here, but across the queries, Bodo was average of 23 times faster, actually median of 23 times faster, up to 65 times. And these kind of numbers essentially mean over 90% savings on infrastructure costs For example, if you are paying $100,000 to AWS, you would be paying just 10,000. So a big difference in infrastructure cost. So this is pretty exciting, I think, to be orders of magnitude faster than Spark, but just Python, not Java or Scala. So we compared versus Dask. Dask is not built for these kind of big data problems, ETL, feature engineering, those kind of machine learning data processing things. I think it's better suited for scientific computing where you have completely independent tasks because communication is difficult in Dask. But what was surprising was that Dask couldn't even load the terabyte data set on this 3 terabyte memory cluster, and it was running out of memory. So we scaled back the data set size to just 100 gigabyte, which is a fraction of the available memory, but that's what Dask could handle. And for these type of things, we found Dask not to be suitable at all. Bodo was 150 times faster on average. You can see the numbers, 88 seconds versus half a second. And there were some cases, query 21, Dask was hanging, and we had to actually search on Google, Dask hangs, what to do, and we saw a bunch of results. So this seems to be normal. But for something that Dask essentially hangs, Bodo solves the problem in under a second. So there's a huge difference, and we don't think Dask has a long way to go to catch up to Spark, and I don't think Dask is capable of HPC with MPI in this current design. We tried to compare to Ray with the mod-in package they have for data processing, but we couldn't load anything more than 10 gigabyte to memory. So we may be doing something wrong. It may need some configuration. We will publish the exact details of versions and whatever we did. So please help us how to see how we can run something. But in general, Dask was originally built for reinforcement learning, and for data engineering and big data workloads, seems like it's not ready. But what I wanted to mention is that task scheduling systems have limitations compared to HPC systems. And there are certain overheads that cannot be avoided. So we believe the ceiling for their performance is Spark, which took years of development to kind of work around the distributed system issues. But still, Bodo is faster than Spark. We think an MPI-based HPC solution is the best for data processing for big applications. So just a quick benchmark for one of our customers before I show a quick demo. They were running Spark for their data pipeline.
Sorry to interrupt. We have 5 more minutes, so just to let you know, if you want to switch up and also take questions, you have 5 more minutes.
Sure, definitely. So for this use case, a real machine learning data pipeline, we were over 12 times faster, and a huge saving for their Azure bill, and they can do real-time machine learning and analytics for their business units now, a real kind of retail customer. So with that, I would like to show you a quick demo on the Bodo Cloud platform. You can install Bodo from Conda on your laptop, a free version, and you can get on our managed cloud service. And here you can create clusters in your own AWS account, attach notebooks to it. I already have a cluster of 4 workers, each with 8 physical cores, so 32 total cores. I'll open the notebook. And I'll show you a quick example where I generated some random data, just some date time, just a single column. And in regular Python, doing a transform with apply, just writing custom code that Pandas can't just call a canned C library or Python library. These sort of things really need compilation. So in Pandas, this takes 21 minutes. I can't run it right now, we don't have time. But with Bodo, just adding this JIT decorator, Bodo understands all of these APIs. You can see what APIs we support in our documentation. So you add the Bodo JIT decorator, and Bodo compiles this apply function to native code with LLVM in the background. It takes 5 seconds. So 20 minutes to 5 seconds. And then you add this PX magic in Jupyter, And using IPy parallel, it came down to 0.15, all the way from the 20 minutes that was Python. So huge improvements with Bodo for these type of difficult data transformation. And all the data processing things like join and group by with user-defined functions, all of these things are supported in Bodo. So you can use SQL. We actually have a SQL solution as well, or just Python for all these difficult tasks. With that, thank you very much. I would be happy to answer questions.
Excellent. Thank you so much for the great talk. I think the first questions would be from, I think you already answered that around limitations. So I'll jump to the second one, which is from Adam Kinsey. So Adam is asking if Bodo is not driver executor, how does it handle processes that are fundamentally non-parallel or which have sequential dependencies?
Data processing operations like join and group by and things like that, they all have parallel semantics, and Bodo analyzes the code, the whole program, and figures out what operations can be parallelized, what operations cannot be parallelized. If something can be parallelized, Bodo is able to parallelize that, but some data structures shouldn't be parallelized. So there are dependencies. Bodo automatically figures it out and replicates those data structures. If it's not possible, there's a problem in the program, Bodo will let you know for sure, right? And you have to change something in the program. Bodo doesn't have any limitation compared to those driver executors. Those driver executor systems are essentially approximating what Bodo is doing. So they are not doing something extra for these type of workloads.
Excellent, thank you. We have another question from Alex. Alex is asking, seems like Bodo is commercial besides a community license. Why not open source it? What are the advantages, disadvantages for going commercial for this type of project?
We do use open source, and if you are interested in contributing to this technology, please contribute to Numba. I'm a developer of Numba as well. We are always looking for contributors, and contribute to MPI or Arrow and these kind of open source projects, or IPython Parallel. We are sponsoring IPython Parallel. So we are sponsoring open source where possible, but we keep something closed source, the core of the engine, because AWS. If we don't do that, we can't make money. And we have seen a lot of problems with having the core of your system open source. So the business model doesn't work. If you know a business model that would let us compete with AWS, let me know and we will open source whatever we
can. Excellent. That sounds like a good promise. Well,
but in terms of, I just wanted to mention we have a community edition on 8 cores on your laptop for free trial on our platform, and let us know what you think. Thank you very much.
Excellent. Thank you again so much for the great presentation, and thank you everybody who asked questions.
Thank you very much. I appreciate it. Bye.